So hello everybody. Hello. Welcome to our next edition of Astronomy on Tap.
Yes.
Yeah. So tonight we have a crossover episode. We have astronomy and the history of science. So we have two speakers, and the first one is Divna Manolova. She's a researcher in the history of science and Byzantine studies as SYRTE, Paris Observatory, PSL, and CNRS. Divna explores how space and dimensions were understood in Byzantine cosmological and astronomical texts and diagrams, and how astral sciences and philosophy were taught in Byzantine times. She has a fellowship for a project called DyAs, or DyAs?
Nobody knows.
Nobody knows, which focuses on lunar and solar diagrams in Byzantine manuscripts from the 9th to the 15th centuries. Her talk will delve into how medieval manuscripts combine narratives with eclipse diagrams, with the conventions they use and the knowledge they convey. Woo!
Thank you.
Yes. The second speaker of the night is Jade Norindr, an engineer at the Paris Observatory. She supervises the development of pipelines to automate the treatment of historical sources in the ADA project. This project started at 2022 and aims to create new ways to study astronomical diagrams from the 8th to the 18th centuries, found in various languages like Chinese, Sanskrit, Persian, Greek, Hebrew, and Latin. It combines the efforts of historians and computer vision researchers to develop algorithms for analyzing these historical diagrams. Jade will discuss using AI and computer vision to analyze medieval astronomical diagrams, from object detection to automatic vectorization, and how algorithms can see, compare, and draw astronomical diagrams. There will be one continuous presentation between first Divna and Jade afterwards. So please save your questions until the end of the presentation and enjoy.
Thank you. Thank you, Sophia. I hope you can hear me. Can you hear me at the back? Okay. Thank you. So if you were here 1 month ago or so, you know that we are trying lots of new things. So last time we tried a new format with these continuous presentations and we liked it. So we are doing this again. This time we are not trying to crossover with the karaoke, as it might seem, but that would be cool too. Maybe after. We are trying this thing to combine regular astronomy on tap, which focuses on contemporary astronomy, astrophysics, cosmology, with history of science. And what we want to do with Jade is to present our work as part of a team that combines digital humanities methods and historians methodology. So I hope we can show you how we do things. I hope you become a fan of this and have fun with us. Since we are a bit technologically challenged, meaning we didn't have a clicker, we are going to give each other signals for each slide that we want to change. So can we move to the next slide, please? So in what I'm going to show you in the first part of the presentation, I want to tackle our common theme. So what we actually are thinking together about is what an image is, in a way, specifically what scientific illustration is. How does this thing work? And if you have been here before, you know that there is always a PowerPoint. Every single person that has presented always has something to show you. And many of you have presented already, so you know you also made your choices to show graphs and pictures and videos and animations. So what I study is how people of the past made these choices and what kind of conventions they used. So that's the first topic. What is a scientific illustration in a way? And then I want to focus specifically on diagrams to tell you a bit about how they work. Then a little bit about astronomical diagrams, and we will finish with one single diagram of an eclipse coming from a 14th century Byzantine manuscript, and we are going to look at its details and see how that goes. So if we go to the first part, let's talk about scientific illustrations and their various kinds. And here is the main question I am asking in my research, and I propose to ask to you. So I welcome any answers if you have them. What is the difference between showing something and telling something? So what is the difference between telling a story, like if I explain to you now how an eclipse happens, and if I actually show you an eclipse? And I think that this is the kind of question that helps us approach what is specific to diagrams and to illustrations, why astronomers or scientists more generally tend to use some kind of image. They don't stick only to text or to data or to numbers or to code, right? There are always this kind of visual aids that we employ. And you can narrow this question or make it more specific when we think about diagrams to think what do they show. So how are they different from a photo, for example, or a graph or a table? And how do they do what they do? How do they operate? So if we move to the next slide, maybe I should be here so we don't lose eye contact. I jumped a little bit. So this would be the second set of questions I want to offer to you. So also, how do we define what a diagram is? It's easy to ask what it does, but how do we define diagrams? And here there are lots of members or some members of our team in the back, and they know we have continuous discussions of what a diagram is. We haven't reached a consensus. So how do diagrams do what they do? I think this is easier than what a diagram is. So one thing that I think we can agree they do is that they deliver, maybe I'm too close to the console. Maybe. So one thing they do is that they deliver their message in a concise way. So in a very compact image, I still hear maybe it's this one. Okay. Maybe it's better now. Okay, yeah, I think it's definitely better. So something that they can do, which text doesn't do so easily, you know how narratives work, they start from the beginning and they end at the end. They take their time. Everybody who has read a book knows that. So with images, they work completely differently. You see them synoptically at the same time. So you look at the image and you see the whole of the image. Then you may focus on details, you may read it as it were, but actually you can see all the information in one instance. And this is something diagrams can do very well. In this one that we are going to see continuously, so you are going to learn with precision its details, it's a diagram that shows at least two things. So it shows you an eclipse of the moon, not of the sun. Maybe I can try to show you. So this is the sun on the bottom. In the middle is the Earth, because this is the medieval period in Europe, so we have a geocentric system. The Earth is in the middle. You have the Earth projecting a shadow, so the dark triangle you see is the shadow of the Earth, a conic shadow. Okay, thank you. And that would be how the eclipse occurs. The moon enters the shadow of the Earth. But you can also see in the middle register there several lunar phases. And perhaps the easiest one to see is this little one here, which is the lunar crescent. So it's a diagram that tries to explain to you two things about the moon, how a lunar eclipse occurs and how the phases of the moon also happen. So this happens in one single image. And I don't know, I'm losing the sweet spot, but hopefully it's okay. No. Now? No. I think it will. Oh. Okay. No problem. So yeah. By the end, this will be perfect. So when we do the karaoke crossover, will be brilliant. So don't worry. Another thing that all our diagrams do, they use a geometrical idiom. So you can see there are circles, there are lines. So this you know also from your own geometry classes, even if you're not doing that today. You have all done a drawing like this at some point. Then they can also use letters. So you remember things like from school, like, you know, if you draw a line from A to B and then a circle from C to D to E, etc. So they can use this kind of labeling, but they can also use full words and phrases to designate their objects. So in this diagram, for instance, in the middle, we have a label. It's in Greek, so I won't put too much Greek on you. But the label in the middle says Gi, or Earth. So the label tells me that the circle in the middle represents a spherical Earth. That's another thing I use this opportunity to tell you, the mainstream idea of the medieval European people was not that the Earth was flat. Not really. So this is a takeaway you can go home with tonight. Then you can see they also use colors. So the sun is bright red because it's the main luminary in the planetary system. And it emits light, which when cast on the different parts of the moon, they illuminate those parts of the moon, and with respect to our position, we can see it as a lunar phase. So the red color here has been used to signify what light is, and the dark color, the dark ink, has been used to signify what is not lit. And the thing you see on the outer rim, there are 28 of those. These are labeled as the fixed stars. So these are the stars that you see on the sky in constellations that do not move the way you see planets move in the night sky. They keep their formation. So here again, we have the color used on them to show that they also emit light. And finally, I would like to propose to the question I started with about diagrams and how they operate and what's the difference between showing and telling. So in my opinion, diagrams are hybrids. They both show and tell because they combine image with labeling, with text. They relate to the text next to them, sometimes very strongly, sometimes more loosely. So in this sense, they do both. But of course, as you know very well, there are other ways of showing things, and now we'll go through some of them. So of course, you can take a photo, and this is a photo I've taken with a very simple phone, of a partial eclipse when I was walking in New York years ago, and nobody cared because it was a partial eclipse. But, for me, it was cool. I could see it, and I could take a photo. Of course, you also can have this kind of imagery. So when we talk about exoplanets, maybe some of you have read something about that. Of course, there's no picture of how life would be, but as in this case, NASA commissioned an artist to present how it would look a day on this exoplanet. And you can see the original caption that says, "This artist concept allows us to imagine what it would be like to stand on the surface of the exoplanet TRAPPIST-1F." So even today, in the communication of science to the public, still we believe that imagination is important, and to be able to visualize the concept that people study and that public money is being invested in. So that's actually important, which is why this kind of imagery is also something we do. Now, in preparation for this talk, I asked online for people to send me their eclipses. And I want to show you some of the submissions I got, which are also other types of visualizations. So some people send me actual photos of eclipses. This is the most recent one, the Great American Eclipse. Some of you may have been there and seen it. So you can see it's from Ashley Elliott. She's belonged to Astronomy on Tap in one of the American chapters. So she shared this with me. This actually is from Neil's friend. He put me in touch with through Twitter. So his name is Hari Krishnan Menon. I hope I pronounced this correctly. And it's from a different total eclipse, annular eclipse from 2019, which was observed in India. He sent me lots of images, but I chose to show you this one because, as you see, it's an eclipse. We know there is an inscription that tells us when and where, but by its shape, if you had only some of those shapes, okay, you shouldn't turn that way, we should be that way. So you can say it's not so much different from the way the lunar phases can be shown on a diagram. Now, this is from our colleague who also presented in Astronomy on Tap, Miguel Montarges. He went to the States for the same eclipse. So now he shows us actually images of the eclipse, which are not photographs. These are photographs of what he projected onto this instrument through a sieve or in this box on the right. So this is another way of producing an image, which is different from the diagram and from the photo. Another friend, Ioana Pavlova, she's a cinema critic, so she played with AI and she sent me images which she produced with various prompts. So these first ones, okay, my back, no. Maybe this is not me. Thank you. Is it? Okay, I'm back. So on the AI, this had to happen. So in the first couple of slides, we see images which are produced with AI, but to the untrained eye, they're very similar to the pictures taken of actual eclipses, right? So to the untrained eye, this is not a wrong picture. And then she made some other experiments with different prompts, and now even an untrained eye can say, well, this is not quite right. This is not human-made. This is something different. But I wanted to show them to you because, as you can see here, the AI drew upon, I guess, a database of diagrammatic images. Because you can see also in the next example, these don't look like photographs. They imitate the graphic language of diagrams and charts that we know and we have seen. So I also got this kind of image from Sarah Schneewind, who is a sinologist. I mean, she has nothing to do with astronomy. But I wanted to show it to you because, first of all, it's handmade, so she drew something. Then she chose to cut the upper right corner, so as if eating, the way you have the shadow eating out of the solar disk. She also chose to insert a text in her image, which I will read to you. So she says, I immediately feel that the light is wrong. Then I see that the shadows of the leaves are the wrong shape. She also included this religious element, which, of course, when we talk about medieval societies, religion will be part of the interpretation of such phenomena. So these are the kind of images that are not diagrams, but you can get. So now, yes, let's focus on astronomical diagrams. And here are some diagrams which come from, in this case, it's a 15th century Greek manuscript. And you see, I've juxtaposed them with the picture of the eclipse, of the solar eclipse from 2019. And I wanted to show you this because I want to speak to you about graphic conventions and how they change through time. So in this 15th century example, you see the lunar phases depicted. And you see, basically, you have circles and you have some colors employed. The color is black and yellow. So the zoomed picture is a circle, filled in with yellow. And I guess today, if you ask a child to draw you the sun, they would use the yellow or orange color. In this case, this is the moon. This is the full moon. And below, I cut this from Sarah's image. So she used the yellow to show the eclipse sun. And by showing you this, I just want to raise the question of the shapes and forms. They are the same, but they are interpreted differently, and maybe you really need a label to tell you that this is the full moon, and in fact there is one just above it. And speaking of conventions, I just wanted to show you how they changed over time. So what you see on the right may be more familiar to you because we use it today to represent a three-dimensional sphere. So this is to us clearly a sphere. It has its axis, its poles are signified by letters. So this shape in a medieval manuscript, which preserves an ancient text, it's by Theodosius Ferrix for the Byzantinist in the front. So you can see the convention is very different. There are two concentric circles and the line is extended beyond them. So as you can see, this shape can be replicated in the diagram we already had. So how does this work? Now, we have in blue, it's the outer sphere of our system. So this is where the fixed stars are. And our system is a spherical system in which there is a spherical Earth in the center. The pink circle is the sphere or the path, the orbit of the sun. So you can see they match into the two diagrams. And in yellow, I have outlined the axis, so the central axis of that system. And now we can see how we would imagine this. So we would project it in kind of a 3D environment. So it would be an actual sphere or semisphere here. The constellations will be on its surface, and this central axis will be actually perpendicular to the equator rather than alongside the surface of the page. So now that you know a little bit about medieval conventions, let's go and see some actual diagrams. And you already saw some, but I promised you one particular case study. So I want to start first by saying something that about badly drawn diagrams. So everything I shown you so far, it was nicely done. But some things are also not so good. So in this page, you see on the right, you have a big circle, and inside there are 3 circles which are aligned. So these are, in fact, the spherical bodies of the sun, the earth, and the moon, and that's supposed to be an eclipse. And this is, as you can see, there are no colors. So the only way we know which one is which, because they're all circles, is their label. And this was sent to me by Anne-Laurence Caudano, who is a Byzantinist and a historian of science. And she commented that I am losing. Yeah, she says, I always love the fact that the notion of a cone of a shadow seems so difficult to represent sometimes. So they were supposed to draw a shadow, but they put all the bodies in the shadow as opposed to, just the moon or just the sun. And this is another type of eclipse diagram. So I'm just showing you this to know that there are many, many options. So this would come from, let's say, the level of higher education, so from Ptolemy's Almagest. And both of them are diagrams of an eclipse and how an eclipse occurs. And as you can see, they're totally different. So the one on the left is the one that comes from the Almagest, from the first text. And then the one on the right was designed by a commentator. And you can see one only uses lines, the other uses lines and circles, and both of them use letters as labels, and yet they are very different. And if you were not educated how to read this, you would not understand it. And it's not just you, it's also the medieval reader. This is something one had to learn. And we all learn this kind of conventions anyway every day. And I want to finish with this one that we started with. So to go in a little bit more detail, you already saw how it works. So you already know that the circles represent spheres. So this is how we represent a sphere on the surface of the page. And you already know that the central axis is the central axis of the universe as well. And just in a bit more detail, we can see there is the sun. And you can see it's also a spherical body. It's bright red because it emits light. And there's this symbol inside of it, which is a symbol for the sun in Byzantine manuscripts. And again, it has a spherical body, and this protrusion from it is the ray of light, so it indicates where the light goes, its direction, so it goes towards the earth. And in the middle, as I told you, the diagram does 2 things. So it also includes the lunar phases, which it explains to us simultaneously. And now, if you see it as a whole, here on the left, you can also see in the shadow of the Earth, which this time is correctly drawn, you have as if 3 moons. So you have 3 little circles. In fact, it's the same moon, but shown in 3 different positions because it can be a bit higher, a bit lower. So depending on how it would be positioned, then you would have a total or a partial eclipse of the moon. And I believe that's probably my last slide. So thank you for your attention, and I give the word to Jade.
Yeah, I can hold on. Hi. So you thought you were here to listen to 2 talks about history of sciences, but it was actually an excuse for me to talk to you about computer science. So this talk will be about computer vision, deep learning, and how we can apply them to historical sources to automate some part of the process that, well, Divna talked a little bit about. And I think we're gonna try and see how just automatic process can do the same thing as historians do, and can those automatic process actually do it? And so this will be the subject of my talk. So maybe I should define what's deep learning to begin with. So deep learning is a type of machine learning that revolves around convolutional neural networks. So it's an architecture in computer science that's based on layers, and those layers transform data into features, and those features are extracted to do predictions in the end and to perform some kind of tasks. And so deep learning is all based on this prediction system, and then those layers can be trained and correct themselves, and that's the learning part of deep learning. And so today we're going to be talking mostly about computer vision, which is a specific part of AI that's focused on image sources like video or images, and on certain types of treatments you can apply automatically on those image sources. So I think we can go to the next slides. So the question here is, using computer vision, how can we get from an historical sources, so like a paper, document, or literal manuscript like the Divna showed, to a digital object. So here a totally vectorized representation of a diagram, and which steps can we go through using only automated process to get there. So the first question we ask is, how can an algorithm find diagrams, and how does it seize diagrams? And I'm using this term very loosely here, but so you can imagine the work of a historian. So they have to go through a manuscript and find in this manuscript of hundreds of pages every diagrams there are, which seems like a fine task when you work on one manuscript, but when you start working on like 50 manuscripts, maybe it's a little bit bigger of a task, and maybe you'll want to automate some of that process. So the first thing we do using AI is to automate the extraction of diagrams from those digitized pages of manuscripts. And so we do that using a model that's called YOLO, which means you only look once. And YOLO is an available model. It's an off-the-shelf model, so it's available on the internet. You can download it, and you can use it as is to perform recognition tasks on the images you want. But so, being an off-the-shelf model, YOLO is not very specific, and it's trained on a dataset that's called COCO, which means Common Objects in Context. That's basically a dataset of thousands and thousands of real-life images on which the model has been trained to extract features and recognize objects, like cats, for example. And so the model is trained like that. So we annotate cats on the picture, and we tell it it's a cat, and then we feed it through a training algorithm, and the model learns how to detect cats. But there is a big gap between a cat and an astronomical diagram. And so what we want is to take this very generic model that learns how to detect cats and differentiate them from dogs and sheep and computers and humans and ties and basically everything, and to just train it specifically on historical data to detect historical diagrams. But the problem we have using deep learning on historical data is that, well, for deep learning to work, you basically need a lot of data. And that's, I mean, really a lot of images, like tens of thousands of images. And so we know that those kind of historical images don't really exist in that number, or if they do, well, that would be all of the historical images we have in a corpus. And then if we use them for training, then it doesn't really have a point to train a model to be used on images that won't exist anymore, because we use all of them in training. And so to avoid using all of the images we have on training this model, first we go through a first step of training images on, I swear, very real images of manuscripts. And those are synthetic manuscripts that are automatically generated using an algorithm that's called SynDoc. And so, as you can see here, those are very, very real manuscripts. They are very realistic. Most of the medieval manuscripts look like that, with a lot of planes and voltmeters and everything. But, well, at least using this, we can teach the model to differentiate objects on a page from the background of the page, and differentiate objects from texts. And, well, maybe that's not great, and maybe that's not really historically accurate, but it's a good basis to start training a model. And because those are automatically generated, we can actually generate tens and thousands of them, and then feed them through the model to refine it, for it to focus really on historical documents and learn how to treat those historical documents. But generally, results using the models only trained on synthetic data aren't really great. And so we want to train them on real historical images that are annotated kindly by our researchers here and in the back of the room. So thank you for your work on annotating all of those diagrams by hand. And so after feeding it synthetic images, we feed it real images of historical data, only a few of them, like maybe 8,000, so 8,000 manually annotated diagrams, but that's enough for it to learn or to fine-tune itself and so get better at specifically detecting diagrams, having seen real diagrams in context from historical sources. But sometimes that's not really enough, and so yeah, it sees things that it considers diagrams that maybe aren't really diagrams, and so that's a problem we actually had on the ADA project. So we trained it on a few historical diagrams, and then we got those results. So diagrams are diagrams, but stems are also diagrams, and Chinese characters are also diagrams. Marginalias are diagrams, and letterings, and this weird water stain here, and also this mandrake that doesn't really look like an astronomical diagram at all, but as we know, a vision model doesn't really have any critical thinking regarding its sources, and so it doesn't have the capacity to analyze and say, oh, this is a diagram because I have the knowledge that an historian would have regarding diagrams, and so everything that's a little bit far from the text or in the margins or with straight lines, it learned to identify it as a diagram, which is not really what we want. But thankfully, we can also go through more steps of training, so we can get this model we train. That's not great, but not that bad actually. And then we can train it more, and it's really an iterative process. So learning from the mistakes the model made before, we then train it with specific image to target the errors it made and get it to get better actually at those specific problems. So here I put a page on the top with a lot of Chinese characters and no diagrams. And so we can just feed this page to the model, and then it will learn that Chinese characters actually aren't diagrams, and that it really shouldn't detect them as diagrams, because that's really not what we want. From those extracted images, we can perform many other tasks. So imagine you have a really good extraction model that you get to extract your diagrams. You always have to do some little corrections after because it's never going to be perfect, but you get a lot of diagrams. Like you perform this task on hundreds of manuscripts, and then you get lots of diagrams, and maybe you want to do some research in them, and you don't want to have to manually take your diagram and compare it to all of the other diagrams you have in your corpus. And we can do some things that are called similarity search. So what we do is that we give the model a query image, so just any image of diagram we have, and we ask it to sift through all of the images in our corpus. I think we're back. Okay. And we ask it to sift through all of the images in our corpus to find the most similar one. But we cannot just feed an algorithm any image just like that, and a pixel image compared to another pixel image doesn't really have any meaning for an algorithm. And so what we want to do first is to transform those images into vectors that are created from a lot of the features extracted from those images by the similarity search model. And so we plot those vectors in a space, and then we compare those vectors using the cosine of the angle between those two vectors. And so, which allows us to find which are the diagrams that are the closest to each other in this space. And so we have kind of a universal numerical representation of diagrams that allows us to compare all of the images, even though the images are really different from each other and have really different features. So, of course, the results are sometimes satisfying, sometimes a little bit less, but using some a little bit more precise technologies that I won't go into detail here, you can actually get some satisfying results. And so I put here the result of one of our algorithms. So this center image was our query image, and then all of the 6 images around them are images that were retrieved by the model in a corpus of I'd say 20 to 30 documents as the most similar images in those documents. So I'm not a historian of science. I'm not an expert at the Almagest, which is the document these were extracted from. But just on a visual consideration, those all look quite similar. And then here the historian intervenes and then say maybe those are not really actually the same diagrams, but for the most part, the algorithm did its job and returned some similar diagrams. And so then the historian can just sift through these diagrams and not through tens and thousands of diagrams we have extracted in our corpus. And that's actually the aim of using computer vision on historical sources. It's to accelerate the work of researchers and never to replace them, because actually the automatic results are never good enough to just rely on that. And also an algorithm never has any critical thinking, and so you always need the contribution of historians to tell you what you are actually looking at. After this task of similarity search, you can be happy with that. You can write some articles on that, and you can be happy with those results because it's already some results you can exploit scientifically. For example, finding diagrams from different traditions that have the same kind of languages, and then you can compare them. You can see how ideas were reused or theories were reused. I mean, there are a lot of ways you can exploit those results, but because we're talking only about computer vision here, there are some other tasks we can perform to get objects that are even more usable in a digital context. And so there are some tasks to add meanings to diagrams, and those tasks are called vectorization. So the image of the diagram that we get from the extraction I talked about on my first part of this, on the first part of this presentation, you get these like cropped images of diagrams that are extracted from a page, and those are pixel images, so, or raster images. So as you can see here, when you zoom on this image, it's just an ensemble of 50 shades of beige pixels, and it's the only informations those kind of image carry are like the RGB values of each pixel, and then that's pretty much it. But when a scribe draws a diagram, or when a historian analyzes a diagram, it's they give meaning to every element. So they can see that this is a circle, this is a line, this is also a line, and then they can say that it's this specific astral body or this specific trajectory. And so there is a lot of meaning that is added through the knowledge of historians or scribes to those images. But when we digitize them or extract them automatically from those digitizations, we don't really have any meaning that is automatically inputted to them, because again, an algorithm cannot do any critical thinking on those images. What we can do is to perform some vectorization tasks on those diagrams. And so what vectorization is actually is that you start with a raster image like that. So it's a pixel image that's made of the little squares I showed you on the previous slide. And then you use an algorithm that's going to perform vectorization. And so draw an SVG, so vectorize image on top of this image, representing the circles, representing the arcs, representing the lines. And so an SVG is an image that's composed of vectors instead of pixels. And in terms of just using them in a digital context, they're better because you can zoom infinitely on them and they never get pixelated because they're not pixel, but just 2 points that draws a line, or just the center of a circle and then the radius of the circle. And there is already a layer of meaning in this image compared to the raster image, because here you have circles that are identified as circles, arcs that are identified as arcs, and lines that are identified as lines. So it's already better for any kind of analysis to have a diagram that you know is composed of a certain number of circles, of lines, of arcs, and it allows for some comparison on a purely computational level that a raster image doesn't allow. But so this result seems great. this vectorization seems to be perfect, but that's actually not an automatic vectorization. It's an automatic vectorization that was corrected by an historian later to remove all of the wrong lines, all of the wrong arcs that the model drew, because when we get only the automatic results, so we go from these images to these SVGs, which don't seem that bad when you look at them from kind of far away, but then when you notice the details, you see that the model took some creative liberties on what it saw on the raster image and what it decided to draw on the SVG image. So we have some small lines that were added because it detected letters as little lines, and because it didn't know what's the difference between a line from a diagram and a line from an Arabic letter that's part of the labels of the diagrams. And it drew some weird arcs over here instead of just drawing the two arcs on the original diagrams, because the paper is a little bit dirty and there are holes in it, and so it didn't do great on real data. So we still need to fine-tune it and to correct it, and we still need to have historians to intervene on those images to clean them. But hopefully this model can get better, because actually the way it was trained is on also synthetic images, because we also have this problem of a lack of sources and a lack of data to feed the model for the first round of training. And so there is this tool to generate artificial diagrams with circles and arcs and lines that are supposed to look like diagrams, but not really, and that look really more like modern art. And there are no actual diagrams in the dataset of our corpus that look like that, but at least it was trained on those difficult diagrams. But seeing these diagrams, maybe we can guess why it detected many circles where there were only 2 or 3 circles. And so when you get those models that are trained only on artificial data, you always need to refine them on real historical data that were finely annotated by historians to get actually satisfying results. And so just as a conclusion, to recap all of the steps I presented here. So we started from a page of a manuscript that was digitized. So it was a physical object that was turned into a digital object, but through just the simple process of digitization, which adds meaning maybe sometimes to the object in general, like the place it's stored, identifying number, or those kind of things, but doesn't really give meaning to each element of the page. And so we extracted the specific diagram images from those digitized pages, and we got already a digital object that is a pixel image of a diagram, on which we performed some similarity retrieval tasks, so to find diagrams that are similar to this one, that are more or less similar to this one. But so we already put this diagram into context using computer vision, and in the end, we get an automatic vectorized version of this diagram, so an SVG image that has the meaning of 3 circles here, and then the lines in green and the arcs in red. And so those are all of the tasks we performed on this digitized manuscript page to add meaning and hopefully make the work of researchers easier when dealing with a lot of historical sources. Thank you. Okay.
Oh, let's thank again, speakers.
Thank you.
That's some question. Wow. This, how do you do it? Do you have any questions from the audience? Yes? 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 Yes.
So, yeah, thank you for your presentations. It's a very different topics from astrophysics, so it's good to see other, like people working on astronomy, but on a totally different landscape, let's say. So it's more of a curiosity question. So and it's maybe more. So were there some, in the diagrams and the way we represent things, were there some strong differences linked to the historical events or discoveries of things, strong differences between different places and things that was maybe more intriguing for you? Or just could you comment on that? I'm curious. Thanks.
Yes, thank you. I think it can be a question for both of us actually, because I'm a specialist in one culture, but Jade has to see what each one of us, and Scott is sitting right there, he's specialist in a different culture. So we are all bringing our material to the team, and we see on the one hand, we see a kind of shared tradition across some of those cultures, which I guess became shared already across Europe and Asia and let's say North Africa, let's say from the 2nd century, by the 2nd century after the Common Era, it was already shared. So certain types of diagrams were already there, and you would see them in Sanskrit manuscripts, and you would see them in the Greek and in the Arabic. At the same time, there are many differences, and when we compare to the Chinese material, for instance, we see it depends when we look at when the Chinese materials come from. Before the Jesuits went there, and this is another colleague of ours who works in that, Ji Chen. So before European, let's say, knowledge was brought eastward and changed the kind of conventions used in the type of astronomy practice, or before. So in a way, you see shared elements, and sometimes you see also very different things. And it's misleading in some senses, because very often we say, I cannot read it, but I know what it is. And half of the time we are right, but the other half we are wrong, precisely because we cannot read it. So I guess it's a very general answer, but this is what I can say. And in my material, being a Byzantinist, the change you see is basically maybe starting from the 13th century, but very strongly in the 15th century, you see many new types or solutions which were brought from Western Europe or from Persia through the translation of texts from eastwards and westwards. So basically, once things get to travel, people, books, and ideas, you start seeing changes in the diagrams too. And I don't know if you have seen everything, so I don't know if you want to say something.
I'm not sure I have anything to add to Divna's comment on that, but I just say that knowing that there are a lot of difference, a lot of shifts between different cultures in the way they represent things and in those diagrams and in those texts, we already actually know that, and that's the base of what we work on, but actually finding similarities is a lot more difficult, because then you need to have knowledge on all of those materials that are not your specific subject of study you worked on, and you have a lot more sources to compare, and you have a lot more languages to explore, and finding actually the circulation of ideas and how these traditions are connected to each other is what we're interested in, and is not an elementary part of our research. It's not like obvious that things are connected, and that's what we're looking for, I think, in AIDA mostly.
Thank you.
Thank you so much for that. I was wondering, the digitization stuff was really interesting. I was actually wondering what the digitization, how that is used in research. I was wondering maybe how's that affected your research? What happens after things have been digitized?
You start.
So I'm not the one using the source materials, so I think that's more of a question for Divna on how it impacts her practice of history and art history, I guess. But for us, at least in terms of computer science and computer vision, that's a lot of data available. Very pragmatically, it's very expensive to digitize the documents, and for a research program like ours, we do not have the funds to digitize documents, and so we know we can rely on those digitized sources to perform a massive computational task like we do, but that's in terms of like the general availability of data and we see in the digitization that there are a lot of lacks in some traditions, depending on how what are the politics of the country regarding digitization of their heritage, and that's a lot of things we have to take into account. Like, for example, we have a lot of trouble finding Chinese sources that are open source or Indian sources that are digitized, just because of like Sanskrit documents are really difficult. But it just depends on the policies on like how to preserve their documents, and if digitization is seen as a necessary step for preservation or not. And yeah, that's for the at least computational report.
Yeah, I guess we cannot do any of these things if the manuscripts were not digitized. I cannot, well, I maybe I'll explain this with a story. So I remember many years ago when I hadn't seen a manuscript in my life, but I got money to go and see some in the Vatican for the first time. And I spent a month there. And until that moment, I've been only reading the paleographers. And in Byzantine studies, many of them are Italian and Rome-based. So then I went there and I discovered, this is a library which is for free. It's difficult to get in it, like you need a recommendation, but once you're there, it's for free and they have everything. And they gave me everything. And when you ask for an article in a journal, it took 3 days to get that journal, but I asked for a 10th century manuscript. Yes, sure, here, it was like that. So the fact that these things are, and this explained to me, why so many paleographers' work or paleographic work was coming out from those places where people could access directly the manuscripts, and they made lots of discoveries and observations. And those of our colleagues, let's say those who live in Argentina and want to work on this material, they have no chance, like they have to do it through digitizations, because it's very expensive for them to travel to archives. And even when things come from India or or China, they often end up in European archives, and you can imagine the story why they have ended up there. So on the one hand, the digitization really became a democratization, of knowledge, that now everybody could look at the manuscripts and find things in them. But then there was a new level of politics, which is really the open access policy. And some libraries are very open about their data, and they allow you to use what they have digitized. Others, not so much. And they make a lot of money out of research funds we actually get from public funds to pay for those image rights. So now there is this aspect which also doesn't allow us to use some of those digitized manuscripts, though they are digitized, but because they are not openly available to be used and reused by researchers, you can kind of look at them, but not really use them for the kind of trainings we did. So that's, I think that's one problem we face. And another problem would be, as maybe some of you know, maybe half a year ago, the British Library was hacked. And ever since, I don't know why, but it was a big thing. Everything, and it still is a big thing. Everything stops. So basically, only recently the catalog was made available. But basically, they are opening little by little their data because the security breach was really severe. So everybody who relied on things being online, because they were, suddenly they're not. And you cannot even find them. So there is this other thing about the practice of research also, that you get used to things being available and then they're not. And of course, final point, different libraries and institutions do digitization differently. And some is good and some is not so good. I don't know if you want to comment on that, but...
Yeah, we have some really high quality digitizations, like in color and everything, but sometimes libraries digitize their documents, like, I don't know, 20 years ago, and it's on microfilm and it's black and white, and it's the only digitization we're ever going to get. And it's a different story working on like poorly digitized documents and high quality documents, but we actually have to accommodate on all of the disparities between the digitization process of the libraries when working with the data. But that's part of working with like real physical sources, I guess, even though those are digitized documents.
Do we have more questions?
Wow.
Thank you very much for your presentations.
Thank you for laughing at all our jokes, because I could hear you.
Yeah, I have a question about the vectorization of these diagrams, because as Divna mentioned, the labels are really important in a lot of diagrams. So you mentioned that sometimes the machine will accidentally use something from Word, but would we eventually like to get to the point where we can vectorize the labels as well, so that those are part of the diagrams?
Right on the money.
It's actually a big question for us because the researchers from our project really want us to find a way to incorporate those labels into the vectorization. But working with text from images using computer vision is really a different story than working with circles and lines. And so there are things that are called OCR or HTR that are meant to transcribe text and then just have a digital version of the text, so like computer characters that you can read. But the problem we have in our project is that Divna works on Greek and Scott there works on Arabic, and then we have some people working in Latin and Chinese, and those kind of models are often really focused on one language, obviously because of the material you have and the expertise you have in working on this corpus, and so there isn't generic solution to this label problem for now. And so mostly what the vectorization process did was to remove those labels to actually be able to vectorize freely the geometric elements of the diagrams and not being troubled by those labels. But we'll be having someone on the project working on those labels soon, probably. So maybe in 6 months or 1 year, it's going to be a different story. I don't know.
I will take a note of that. In 6 months or 1 year.
In 6 months.
Two questions completely unrelated. First question, when you trained your models, has the model ever detected something which an actual archivist didn't see themselves? And the model picked something up and you had to study it. And the second question is, do you include, pirated archive material in your archives? So, if you sneak into the archives, take a picture without permission, and you process that data.
This could be on YouTube.
How important is, pirated open source data for archival like this?
Since this is going to be on YouTube, we will speak in hypotheticals. Allegedly.
So, allegedly, a researcher from our program asked us if we could, maybe, by accident, just slip a document from a library near Rome that I won't cite, which has not really any open access policy, but has a lot of digitized documents inside of our corpus. But we said no, because that's going to be a lot of problems. Even if it's allegedly, it's going to be a lot of problems for us later. And it was a discussion because indeed there is a lot of material that is not open access, but what we really want to do in the project is to create models that are off the shelf, that are made available for everyone to use. And so we really need to make sure that our data are really open and clean and everything from each step of the training process. We find ways to to make it work.
The algorithm finds.
And so during the training step, the question about finding things that we hadn't seen before. So the first time we did some training, every researcher annotated data from their own data set, from their own specialty, and we hadn't really uniformized the process of annotating. And so we got the training data, the training results that weren't really that great for training, but we didn't have a lot of sources. And then when we went back and looked at the data, we noticed that some diagrams weren't annotated. And then when we asked the researchers why were those diagrams weren't annotated, they answered that, well, if Ptolemy was here in the room with us, he wouldn't consider this diagram an astronomical diagram, and so we shouldn't annotate those diagrams that Ptolemy from the 2nd century wouldn't recognize as astronomical diagrams. And so with the training results, we saw that we had a lack of uniformity in our data. And then the next time we did the training, every researcher annotated data from their own corpus, but then, or PI, went through all of the data we had annotated and annotated the things that people didn't want to annotate because Ptolemy wouldn't be happy with that. So, yeah.
And I can add from my experience of the annotation. So it happened to me that there will be things I would not see because of the, let's say, imagine the manuscript is open and something is like really close to the gutter or to the margin, or, it's very faint. So sometimes I would not see it also because I'm trying to do it in a, fast way. And then the algorithm will catch some of those. It will also catch those that show through the page. Yeah. So then I would have to delete them. But it was helpful because it's those things which are tiny or things that are faint, which I didn't see the first time because I just didn't spend so much time on each page. Now you know. Oh, sorry.
I'll take it into account next time.
So I have a sort of basic question, which is why vectorize? Because it seems like you're adding some artifacts to the diagrams which are not there initially, like perfect circles or something. For example, some diagrams in the first stop are imperfect, bad, but like vectorizing will remove those imperfections. So why vectorize at all? Leave them as they are.
That's actually not a basic question, but a really good question. And the reason we vectorize is because the aim of our project specifically is to produce critical editions of those texts that are in the manuscripts, and so to produce digital critical editions of the diagrams specifically. Yeah. And so to produce those critical editions, it's easier to have a vectorization that's a little bit automated that the researchers can then edit using tool we're going to produce or those kind of things. But we like the diagrams as they are, but because we want to make digital critical edition, then we need to have digital objects we can manipulate anyway, and so that's why we vectorize. I don't know if you want to.
But I can just say that from the researcher's point of view, we had a lot of arguments about exactly what you say. And as we had to annotate for the vectorization, we had to think, do we use a circle? And obviously it's not a perfect circle in the manuscript, or the line, let's say 2 lines do not meet, but that we know they are supposed to meet. What do we do? And it was a big discussion. Then we decided to kind of correct. So we are aware of that, but it was something we had to do to help the vectorization process. But it was not an easy thing. So your question was right at the heart of things. Thank you.
Oh, thank you for the talk. So my question is also, I think you already answered to my question just before. So it's related to the text reading by the program. So my question is assume you are able to recognize the text. So you told you are actually working on to read the text, trying to read. Do you think it will improve, assume you could read the text instead of the patterns. So will it be more efficient to distinguish the text from the reads? So basically you have Arabic letters, so you can train both you can train the machine much better because we already know Latin alphabets, we already know Italian, we already know Arabic alphabets. So will it be more efficient to train the machine in text compared to training the machine in recognizing the pattern, and then find whatever not is text is as a pattern? Will you think that would be a much efficient way, or what is actually done is more efficient? It's just a basic insight that came to my mind. Thank you.
Do you want to start?
No.
Or? Okay. So
I don't know.
I think the first thing is that working on text and images are just two different subjects in terms of historical studies, and there are really good research programs working on text specifically and using AI to digitize their sources and to transcribe automatically their sources. But that's just not what we really want to do here in this project, and that's why we don't actually focus on the text. So before this project, we had a project on astronomical tables, in which we were hoping to do some table detection and then detect the cells in those tables and then transcribe the numbers in those cells to get digital version of those tables using a little bit of HDR. But actually, even if we train the model to recognize and transcribe the text, we would still just get like text files of the content of those manuscripts, and we would still need researchers to analyze them and to find the meaning in this text. And so that's just a different field of history, I guess. I don't know if you want to...
But just from my experience, of course, what you are saying could be ideal, but working with the digital humanities part of the team, I learned that actually it takes a lot of time and effort to do each of those trainings. So if we wanted to do text and image, it would be, I mean, we would never finish, and now we actually have done certain steps and have some results. Okay. So on the other hand, there is the open aspect of this kind of research. So there are existing projects that we can later on, use know-how from to do that. And in a way, I calm myself, to be at peace with the situation, thinking about the medieval scribes also, because very often, though not always, you would have a differentiation of labor. So one would be the person who writes, who is trained to write in a certain script and writes the text, and a different person will be trained to execute illuminations, diagrams, illustrations, whatever. And in the material I study, for instance, in the 14th century, you start getting this kind of scholars who are good enough but don't have the money to pay the specialist. So they start doing both of those functions because they cannot afford the professional scribe. So thinking of those, people and their manual labor, I am at peace with the fact that, from a computer science point of view, it's not so easy to do both, and maybe we just do one step at a time for now.
There are some things that were obvious for the people who draw or design or wrote the things back then, and now it's not obvious to us because we don't have the symbol has changed or whatever things, but we lost the meaning, and so it's hard to, like, something that were not explained because everyone would have understood by then what it means, and now we are back in the meaning.
Well, I think even then, not everybody would understand, so very few people. And then, as I try to show you, really the convention changes, and it's really about the way, from what we see in these diagrams, because it's about astronomy, so you are always in this kind of spherical universe, which means that you are talking about spherical objects in space, but on a flat surface. So the whole graphic convention they employ is how do we put something that's three-dimensional and spherical on a page, and if there are relationships between different points of that sphere, how do we graphically represent it? So I think that's the main change, that now, or from the 16th century onwards, the representation of the sphere is different. And also one question we've been asked before is, for instance, did we ever see ellipses? So we don't see many. So the idea of the elliptical shape when applied to the astronomical content is really coming later, for instance. So that's what I can say.
Do you have more questions? Can I ask you some questions? I'm just curious because the first diagram you showed about the lunar eclipse,
yeah,
and the representation of the celestial,
the stars.
Yeah, they were showing half light and half shadow. And I'm very curious, did they think that the back of the star was dark, or what would they run? What way did they gives that as a diagram for a star.
Well, first of all, it's a very rare type. I don't know any other image like that would differentiate between the stars. And some of them, not only like the back is dark, the front is light, but for some of them were filled in entirely in red and some were just outlined. So my working hypothesis about this is for the light part, not that they didn't think that a star only emits light from one part of its surface. No, that they thought it emits light in general, and it's a kind of a spherical body, and all the celestial bodies are not solid, but rather kind of gas-based, air-based. So they are all spherical. They are kind of rarefied bodies that emit light, and the reason I think on this diagram the face towards the center is depicted as lit is because it puts an emphasis on the viewers, on the viewpoint of us, the observers. So in the middle is the Earth, and the point is, what do we see? We see an eclipse, we see the lunar phases, we see the stars. So I think the color is there to say where is the viewer. The viewer is in the center. That's what they see.
It's a similar but maybe slightly technical question. When looking at the diagram of having the Earth in the center and the Sun here and the Moon here, I'm not convinced that could explain the phases of the Moon. Like given the length of the day and sort of thing, is that something we understand? Can you explain the lunar phases?
Maybe which one? So do you mean the diagram which was both eclipse and phases? This one, or the one that was just the phases? The one with the stars?
The stars.
Yeah, so the one that was at the beginning and the end, yeah. So I don't think they have to be accurate. So there are some diagrams that are more, let's say they're more accurate in the placement of the three bodies involved, one of which is the observer's point of view, so the Earth as the observer. So there are some which I think can explain, and do explain how the phases occur and try to emphasize which part of the moon we see, which part is lit, and what is the relative position of the three bodies. This one, I don't think it's accurate, it's aiming to be accurate, but it's aiming to introduce this additional theme as part of the topic of the diagram, but I don't think it's accurate. I think you're right that it doesn't explain correctly how the phases are resulting. But there are some which are better for that.
So my question is, you had said that there's a lot of maybe some backlog in the interpretation and verification of the diagrams that are found by these models. And so I was wondering if you rely on any volunteers maybe from like citizen science projects to help you out and how that impacts your research.
So we rely on our postdocs that very nicely corrects the annotations for us. We rely on researchers that are also working for our project on their own time because they think it can help their research. And so what we do with this algorithm is actually to plan to integrate them to a platform that researcher can use. And so everyone would be responsible of their own sources. So you would upload a witness, so a manuscript, then perform an extraction task on this manuscript, and then correct yourself the results that are imperfect. So it's not an open initiative like
the stagiaire.
And the interns. That's true. You're right. We have interns working on the annotations too.
Yeah.
Do we have any last question? Okay, so let's thank the speakers again.
Thank you.
Thank you so much for coming, and see you in the next one.
Yeah, thank you.